Bismillahirrahmanirrahim. In the name of Allah, the most merciful and the most beneficent. Assalamu alaikum, viewers. I am Kansa Safdar from Department of Chemistry at University of Management and Technology. And now I am here to present a review article on smart technologies in chemical manufacturing, which I done in the supervision of Dr. Hammad. Now, let's start. First of all, look at the table of contents. In this article, I'll discuss first abstract, and then after, I'll discuss its introductory chapter. In this, I'll discuss what is smart manufacturing, how to integrate smart manufacturing in chemical industries, its benefits, and then integrating smart manufacturing into your core system, and then latest trends in smart manufacturing, and then some research questions. And then after this, our second chapter is review of literature. In this chapter, I'll discuss some review articles related to nanoscience and role of smart technology in agriculture industry, role of smart technology in cosmetic industry, and then my chapter 3 is about the discussion of all these articles, and chapter 4 is about conclusion. In this chapter, I'll discuss some job opportunities and future challenges. Now, look at the list of figures which we discuss in this article. Number one figure is about smart manufacturing. Number second, its benefits. Number third figure shows green synthesis. Number four, IoT in chemical manufacturing. Number five is about data analytics. Number six is about advanced manufacturing by using robots. Number seven is about blockchain. And other figures are about second unit, which is number one is flowchart of RGO sensor interface. RGO meaning reduced graphene oxide. And the other second figure from chapter 2 is about data collection at various stages by using blockchain, and then components and application of smart agriculture, and net zero of carbon in future, AI and ML for scale up of carbon dioxide electrolyzers, traditional approach, smart approach to carbon dioxide electrolyzers. And the second last is smart manufacturing inspired face mask. And last is about NFC based smart face mask. Now look at some abbreviations which we discuss in this article. Number one is AI. AI stands for artificial intelligence. SM stands for smart manufacturing. Next is IoT. IoT stands for Internet of Things. Next is IBSNAT, which stands for International Benchmark Sites New York for Agrotechnology Transfer. And then IRRI, which stands for International Rice Research Institute. Then FFP, Filtering Phase Space. NFC, Near Field Communication. Then RGO, Reduced Graphene Oxide. Now, start this article from abstract. Abstract shows about all the research and review of this article, which starts from smart manufacturing encompasses technology that employs interconnected machinery and tools to enhance manufacturing performance while optimizing energy usage and workforce requirements. This is achieved through the application of big data processing, artificial intelligence, advanced robotics technology, and their interconnectivity. This paper aims to provide a definition and comprehensive discussion of smart manufacturing systems, detailing their current implementation status. It further assesses the existing gap between the current chemical manufacturing systems and the envisioned future of smart manufacturing systems. The paper also delves into the associated technologies and their contributions to smart manufacturing. In order to comprehensively address this rapidly evolving field and explore all its dimensions, the paper presents the most recent advancement in smart chemical manufacturing, in nanoscience, in electrochemistry, in cosmetic industry, in agriculture industry, along with an analysis and impacts. The paper also addresses the challenges of implementations, identifies opportunities, and outlines the future directions for smart manufacturing systems. Now, look at the keywords which we used in this article. Number one is Industry 4.0, smart manufacturing, Internet of Things, and artificial intelligence. Now, look at the chapter 1, which is Introduction. The number one point is, what is smart manufacturing? Smart manufacturing is one of the most innovative methods of producing things by incorporating various artificial intelligence technologies such as computer vision, machine learning, deep learning, and so on onto their core manufacturing system. Chemical companies benefit from high levels of adaptability, quick design modifications, and more flexible technical workforce training when they use the smart manufacturing process. Using a smart manufacturing process, they can meet criteria even when they have to make chemicals on demand. How the manufacturing industries use artificial intelligence to enable large-scale smart manufacturing processes will determine how innovative they can become. Our second point is how to integrate smart manufacturing in chemical industries. The chemical sector is capitalizing on artificial intelligence to enhance the chemical manufacturing process, aiming for greater precision and efficiency. Smart manufacturing facilitates the transition from Industry 3.0 to Industry 4.0, making a pioneering transformation within the manufacturing industry. This evolution enables the chemical industry to automate manufacturing operations by employing IoT and machine learning technologies. On a worldwide scale, data indicates that the chemical industry employs over 20 million individuals and boasts an annual sales volume nearing $5 trillion. This industry serves as a cornerstone for various sectors, including agriculture, pharmaceuticals, automotive, and construction, all of which rely on diverse chemical products for their operations. Now, this figure shows integrate smart manufacturing in chemical industries. So consequently, it is of paramount significance for chemical industries to revolutionize their manufacturing processes as they play a crucial role in supporting a wide array of other industries. This is achieved through the adoption of cutting-edge AI-based technologies such as IoT, machine learning, computer vision, big data, and many more. Third point is benefits of smart manufacturing. Now look at the figure 1.2, which shows some benefits of smart manufacturing. Starts from innovation, energy efficiency, productivity, and then product failure detection. Number one is enhanced productivity. Traditional methods of data collection and analysis are time-consuming and less efficient. In contrast, smart manufacturing enables real-time data collection and processing, delivering superior accuracy and efficiency. Manual data capture in chemical manufacturing is prone to errors and consumes significant time. Smart manufacturing relies on the pillars of machine learning, computer vision, and big data analytics provide a seamless and error-free manufacturing experience. Data analytics identifies the necessary data for manufacturing process and optimization is achieved through efficient analysis. Next is energy efficiency. Historically, many chemical industries employed conventional manufacturing methods that were both time and energy wasting. Smart manufacturing, on the other hand, embraces nearly complete automation, allowing industries to automate numerous tasks with minimal energy consumption while maintaining accuracy and efficiency. Machine learning and computer vision algorithms are seamlessly integrated into the manufacturing system to automate critical processes. Next benefit is innovation. Smart manufacturing software incorporates sentiment analysis by soliciting customer feedback to suggest products that are more likely to be well received. Understanding customer preferences allows for product innovation based on customer needs, reducing unnecessary effort, saving cost, and enabling investments in product enhancement. Quality takes precedence over quantity, and smart manufacturing ensures that product quality is maintained during the innovation process. Our next benefit is product failure detection. Data analytics algorithms can detect product failure by analyzing customer sentiments and past purchase and patterns. Understanding product demand and performance insights saves time and money, contributing to the development of effective product marketing strategies and precise customer targeting. So, why choose smart manufacturing? Smart manufacturing stands at the forefront of technological advancement in manufacturing sector, enabling companies to build and innovate products tailored to customer requirements by predicting product demand and manufacturing accordingly. Smart manufacturing optimizes production cost, ensuring high efficiency and accuracy. Sensors promptly detect issues and provide timely alerts. Predictive analytics anticipates problems before they manifest, mitigating financial cost. Unlike traditional manufacturing processes that prioritize economies of scale, modern smart manufacturing leverages various AI technologies to enhance the manufacturing processes, ensuring heightened accuracy. The next point is how to integrate smart manufacturing into your core system. To implement smart manufacturing within your organization, you must seamlessly integrate your existing manufacturing system with cutting-edge AI solutions. Smart manufacturing encompasses a wide range of technologies. You should seek solutions that can completely revolutionize your manufacturing processes. Begin by identifying companies offering such solutions and establish connections to explore the potential for transferring your manufacturing operations. Number 50 is latest trend. What are the latest trends in chemical manufacturing? Here are some trends. The chemical manufacturing sector is in constant state of evolution, characterized by the emergence of novel technologies and processes tailored to meet the demands of an ever-changing global landscape. As pressing global issues such as climate change, resource scarcity, and sustainability continue to gain significance, the chemical manufacturing industry finds itself compelled to foster innovation and develop fresh technologies aimed to addressing the challenges. In order to succeed, it is imperative for your company to effectively manage change and progress. Understanding your present status and setting clear future objectives are essential steps in this endeavor. So within this guide, we furnish an informed overview of chemical industry designed to assist organizations in attaining their goals. Number one, look at the green chemistry. Green chemistry is of paramount importance in chemical manufacturing due to its far-reaching environmental and human health implications. Embracing the principles of green chemistry enables companies to curtail waste and emissions, conserve resources, and produce safer products. This can be achieved through various means, including development of more efficient processes that generate less waste, the utilization of renewable feedstocks, and a reduction in solvent and auxiliary substance use. These practices significantly reduce waste and emissions, lower energy consumption, and trim cost. Figure 1.3 shows some grain synthesis. Additionally, grain synthesis leads to the design of safer chemicals and products, decreasing the use of hazardous substances, fostering product degradation and non-toxic components, and minimizing the risk of accidents and chemical releases. This results in enhanced work safety, reduced cost associated with accidents and environmental remediation, and contributes to a more sustainable chemical manufacturing landscape. Now look at the Internet of Things, which is IoT. The IoT has become an integral component of chemical manufacturing, enhancing efficiency, productivity, safety. It also the interconnection of devices, sensors, and objects to the internet, enabling real-time data collection analysis within chemical manufacturing. IoT finds application in equipment and machinery condition monitoring, ensuring timely maintenance to avoid breakdowns and costly repairs. Figure 1.4 shows some IoT in chemical manufacturing. It also plays a vital role in real-time product quality monitoring, facilitating early issue identification, resolution, reducing waste, improving waste product consistency. Moreover, IoT aids in optimizing production processes by collecting data on factors like temperature, pressure, and flow rates, efficiency, and trim cost. Beyond efficiency and productivity gains, IoT contributes to safety by monitoring potential hazards, preventing accidents, and reducing worker risk. Next trend is data analytics. Data analytics is increasingly pivotal in chemical manufacturing, enabling manufacturers to collect and analyze substantial data volumes in real time. This empowers manufacturers with insights spanning raw material procurement to product quality control, promoting optimization of production processes, reduced cost, heightened product quality. Data analytics aids in production process optimization through data collection, analysis of key factors, enhancing efficiency, reducing cost, ensuring product quality. Moreover, data analytics assist in equipment monitoring, enabling the detection of potential issues prior to their occurrence, reducing downtime, and preventing costly equipment failure. Additionally, data analytics supports supply chain management by analyzing supplier data, identifying areas for improvement, enhancing procurement decisions to curtail cost, improve lead times, and ensure a reliable raw material supply. Now look at the figure 1.5. It shows data analytics used in for product quality. This technology further aids in real-time product quality control, facilitating issue identification and corrective action to reduce waste, enhance customer satisfaction, and boost profitability. In sum, data analytics is poised to revolutionize chemical manufacturing by offering real-time insights, optimizing production processes, reducing cost, and improving product quality, all leading to increased profitability and competitive edge. Next trend is innovative materials. Innovative materials are increasingly pivotal in chemical manufacturing, enabling the development of novel products and production processes that are more efficient, sustainable, and cost-effective. These materials are characterized by unique properties and performance characteristics not typically found in traditional chemical manufacturing processes. Examples include graphene, one-atom thick carbon material uses catalyst, barrier materials, and electronic device component. Another example is bioplastics derived from renewable resources. Serving as sustainable alternative to traditional plastics, innovative materials also facilitate the creation of new production processes that are efficient and sustainable. Ionic liquids, for instance, are used as solvent in chemical reactions, offering advantages, low toxicity, and high selectivity. Innovative materials offer the potential to transform the industry by reducing environmental impact, introducing products with unique properties, and enhance competitive market positioning. So our next latest trend in smart manufacturing is advanced manufacturing by using robots. Figure 1.6 shows advanced manufacturing by using robots. Advanced manufacturing is pivotal in chemical manufacturing, enabling faster, more efficient, and precise production. It encompasses cutting-edge technologies like automation, robotics, additive manufacturing to enhance production processes. Automation improves efficiency, reduces labor cost, and prevent human errors. Robotics performs complex tasks, enhance precision, and carries the quality control checks. Additive manufacturing or 3D printing creates integrate shapes, structures attainable through traditional methods is used in creating new product and improving existing ones. Advanced manufacturing layers to improve efficiency, reduce cost, heighten product quality, providing a competitive advantage and improved customer satisfaction. Next is blockchain. Blockchain is also a very trending in chemical manufacturing. Blockchain technology offers decentralized, secure, and transport transaction and data recording with applications in chemical manufacturing. It enhances supply chain transparency, promotes product traceability, and augments data security. Blockchain ensures that all parties in the supply chain access the same information, reducing fraud risk and fostering trust. It facilitates a product traceability to recording data on product origin, quality, and movement throughout the supply chain, enabling quick issue identification and quality control enhancement. Figure 1.7 shows blockchain. Additionally, blockchain technology enhances the data security, reducing data breach risk and improving data privacy. Implementation of blockchain in chemical manufacturing improves transparency, product traceability, data security, and market positioning and customer satisfaction. Next trend is cloud computing. Cloud computing is a technology that grants user access to shared computing resources, including server storage and applications via the internet. In the realm of chemical manufacturing, cloud computing holds potential to enhance collaboration, bolster data management, and elevate operational efficiency. One application of cloud computing in chemical manufacturing involves fostering collaboration across teams, organizations, by providing a centralized platform for data sharing and communication. And cloud computing breaks down silos and encourages collaboration across various departments, locations, and even different components. This collaborative approach exhibits product development and enhanced decision-making processes and reduces time to market. And other utilization of cloud computing is in the realm of data management. Storing data on cloud servers bolsters data security, mitigates data loss risk, enhances the data accessibility. Furthermore, cloud computing enables the analysis of large datasets, generating insights that inform product development and process optimization. Cloud computing further enhances operational efficiency by employing cloud-based software applications that streamline operations, automate tasks, and reduce the need for manual intervention. This led to cost reduction, quality improvement, and increased productivity. In summarize, the implementation of cloud computing in chemical manufacturing processes the potential to revolutionize the industry by boosting collaboration, optimizing the data management, and enhancing operational efficiency. By embracing cloud-based technologies, manufacturers can gain a competitive edge in market better to aids of their need customers. The next trend is artificial intelligence. Denotes ability of computer systems to perform tasks that traditionally necessitate human intelligence, such as perception, reasoning, and learning. In the realm of chemical manufacturing, artificial intelligence holds the potential to enhance process optimization, accelerate product development, and elevate operational efficiency. Artificial intelligence contribution to process optimization is evident through the utilization of AI algorithms to analyze data from sensors to other resources. Manufacturers can identify patterns, predict outcomes, and optimize process parameters in real time, ultimately reducing waste, enhancing product quality, and boosting productivity. Artificial intelligence further aids in product development by employing AI algorithms to analyze large data sets. Manufacturers can identify new product opportunities, optimize product formulations, and accelerate product development cycles. This accelerates the introduction of new products to the market. Operational efficiency gains through AI include AI-powered systems for scheduling, routing, and other tasks. In summary, the implementation of AI in chemical manufacturing has the potential to transform the industry by enhancing process optimization, accelerating product development, and elevating operational efficiency. By incorporating AI-powered technologies, manufacturers can gain a competitive advantage in market better cater to customer needs. Our next trend is nanotechnology. Nanotechnology pertains to the design, production, and application of materials and devices with nanoscale dimensions. In chemical manufacturing, nanotechnology holds the potential to enhance product performance, reduce waste, and bolster sustainability. Enhancing product performance involves incorporation of nanoparticles into products to augment of physical and chemical properties such as strength, durability, conductivity. This leads to the development of innovative products, including lightweight and durable composites, efficient batteries, and high-performance coatings, and also reduce waste. Reduction of waste is another aspect of nanotechnology in chemical manufacturing. By utilizing nanoscale catalysts, manufacturers enhance the efficiency of chemical reactions, thus reducing waste generation. This results in cost reduction, improved sustainability, and reduced environmental impact. Sustainability is further achieved through utilization of nanoscale materials and devices to develop energy efficient, environmentally friendly, and sustainable products. Examples include new solar cells technologies, energy storage systems, and wastewater technologies. Overall, the integration of nanotechnology in chemical manufacturing has the potential to revolutionize the industry by enhancing product performance, reducing waste, and bolstering sustainability. By adopting nanotechnology, manufacturers can gain a competitive edge in the market while reducing their environmental footprint. Next trend is cybersecurity. Cybersecurity encompasses the measure to protect computer systems and networks from unauthorized access, theft, damage, and other threats. In chemical manufacturing, cybersecurity is pivotal for safeguarding sensitive data, preventing operational disruptions, and ensuring regulatory compliance. Implementing cybersecurity measures involves the use of firewalls, antivirus softwares, and other security technologies to prevent unauthorized access to computer systems and networks. This protection extends to safeguarding sensitive data such as intellectual property, trade secrets, and customer information from cyber threats. Some data security is further strengthened through encryption, ensuring safety of data in transactions. This measure guarantees data remains secure even in the event of interception by a cyber attacker. Employee training and awareness programs are also instrumental in cybersecurity implementation. By educating employees on cyber threats, data protection, best practices, and the identification and reporting of suspicious activities, manufacturers reduce the risk of cyber attacks stemming from human error. In conclusion, the use of robust cybersecurity measures in chemical manufacturing is essential for protecting sensitive data, preventing operational disruptions, and ensuring compliance with regulations. The adoption of these cybersecurity measures safeguards computer systems and networks from cyber threats, upholds customer trust, and secures the long-term sustainability of the business. Next trend is mobile applications. Mobile applications, often referred to as apps, are software applications designed to run on mobile devices like smartphones and tablets. In chemical manufacturing, mobile apps have the potential to enhance efficiency, improve product quality, and increase productivity. The adoption of mobile solutions in chemical manufacturing brings about changes in the workplace environment, enabling more efficient sales, supply chain, procurement, and asset management. Mobile technologies establish connections between from the MS of business, machine, material, manpower, and market. Mobile applications facilitate asset management, and business should consider embracing these technologies based on the specific needs. This incorporation of mobile technologies benefits the chemical industry through quicker response and tracking severe business application and collaboration. One application of mobile apps in chemical manufacturing is the enhancement of process efficiency. Real-time data collection from sensors and other sensors enables manufacturers to monitor and analyze process parameters, proactively identifying potential issues for faster and more effective responsive time. Now, look at some research questions which we discuss in this article. The number one is the chemical industry will adopt Industry 4.0 in what ways? What are the benefits of adopting Industry 4.0 technology in chemical manufacturing? How is sustainability impacting the chemical manufacturing industry? And number four question is, how is safety being addressed in chemical manufacturing industry? Now, we will discuss the chapter 2, which is a review of literature. Let's start with review of smart technology in role of smart technology in nanoscience. So Muhammad Ali and some other researchers researched at in 2023 worked on the production of graphene nanoparticles as data generating digital materials in Industry 4.0. One potential application of 2D, two-dimensional materials lies in augmenting the multifunctionality of structures and components utilized in aerospace, automotive, civil, and defensive industries. These multifunctional attributes encompass sensing, energy storage, EMI shielding, and property enhancement. Within this article, we have delved into the potential use of carbon and its variants as data generating sensory elements within the framework of Industry 4.0. We have laid out a comprehensive roadmap encompassing three emerging technologies: advanced materials, artificial intelligence, blockchain technology. The untapped potential of 2D materials such as graphene nanoparticles and serving as an interface for the digitalization of modern smart factory. Often referred to as the factory of the future is explored. The article delves into the role of 2D material enhanced composites as intermediaries between physical and cyberspace. It provides an overview of the integration of graphene-based mass embedded sensors at various stages of the composites manufacturing processes and their application in real-time structural health monitoring. This article also addresses the technical challenges associated with interfacing the graphene-based sensing networks with the digital realm. Additionally, it offers insights into the integration of associated tools such as artificial intelligence, machine learning, and blockchain technology with graphene-based devices and structures. Now, look at the figure. This figure shows a flowchart of RGO sensor interface. RGO meaning reduced graphene oxide. A flowchart is presented illustrating the process of digitizing composite structures by utilizing graphene nanoparticles as an interface to establish a digital factory environment. Within the manufacturing setup for digital manufacturing, reduced graphene oxide-based sensors in junction with conventional sensors can be integrated. This integration enables the attainment of smart manufacturing in the Industry 4.0 framework through the utilization of advanced tools such as blockchain technology, artificial intelligence, virtual simulation, and digital twins. Next point is data collection by using blockchain. How we collect data by using blockchain? Blockchain technology based on the data from reduced graphene oxide sensors offers us secure and traceable means of collecting and managing the efficiently. While AI tools can efficiently analyze the data obtained from RGB-based sensors, a blockchain is essentially an evolving list of immutable records as blocks connected through cryptography and stored on a decentralized network of computer or nodes on chronological order. The use of smart contracts within blockchain technology automates processes in highly reliable and trustworthy manner. This technology is currently extensively utilized in sectors such as finance, banking, healthcare, and supply chain management. In the context of using RTO is a sensing element in manufacturing of fiber reinforced polymer composites. Data is generated at various stages encompassing physical properties and process parameters. These stages from the multi-supply chain, which includes raw materials, manufacturing processes, finished component structures. Data generated at each step with varying nature and format can be efficiently and securely collected and stored using blockchain technology. The collected data includes information directly obtained from RTO sensors as well as data pertaining to the physical characteristics of reinforcement and metrics, along with the data derived from physical and virtual experiment. The data collection and storage process is illustrated in illustrated in figure. This figure shows that the data collection at various stages, from raw materials and process monitoring, in service monitoring, then characterization and post-process monitoring. In addition to that, data directly collected from RG sensors, information related to the physical characteristics of reinforcement and matrix materials is typically provided by the supplier. These properties are subsequently validated and further characteristics as determined through characterization, experiments, and visual simulations using digital twins. Data such as the 3D geometry of the part to be produced, mold designs, and various processes parameters also play a crucial role depending on the chosen manufacturing method. The RGO-coated materials can facilitate in-source data acquisition during the manufacturing process. The inspection of finished parts generates additional data related to part quality such as porosity maps and white content, as well as the tolerance levels. Furthermore, during service, the smart structures employing RGO sensors generate signals related to the structural health, which can be managed in maintenance logbook within the blockchain ledger. Beyond its direct applications, blockchain technology can also assist in creating digital twins and work in tandem with artificial intelligence to have a broader impact. Blockchain technology serves as a secure, large-scale, reliable tool for data collection and management, facilitating the implementation of smart operations using networks of sensory elements, including RGO-based sensor. Now, our second point is role of smart technology in agriculture industry. Now, look at the review article. Don Coley in research in 2022 studied and reviewed smart techniques in agriculture industry in Japan. Japanese farms are currently characterized by a modest yet expanding physical size and annual sales compared with a diminishing and aging workforce. This is growing trend of abundant farmland and large corporations wielding significant capital and managerial influence are gaining substantial assets. In response, the government has outlined plans to enhance the agriculture growth by embracing advanced smart technologies on a large scale, supported by a set of favorable policies and measures. This study examines the features and technologies associated with smart agriculture as perceived by Japanese scholars. It delves into the practical implementation of smart agriculture in Japan, highlighted in case study on the Notch Navi at 1000. Smart rice production model. Findings reveal the Japanese scholars have conducted extensive research on smart agriculture, focusing on regional characteristics by prioritizing labor efficiency, precise management, disaster reduction, and the preservation of traditional farming skills. The government ambitious agenda is sustained by comprehensive policy packaging encompassing project demonstration, support services, environmental enhancement, education and training initiatives, and international outreach. Aligned with the agricultural landscape of Japan, rice production emerges as a crucial sector for the research and application of smart farming technologies, whether in the form of individual technologies and comprehensive model. These policies technologies have proven effective in reducing labor and production cost and simultaneously enhancing profit. Now, next is technological components. In this domain, Japanese scholars undertaken diverse research endeavors, enabling the categorization of fundamental components of smart agriculture into the modules, as depicted in this figure. Figure 2.2 shows components and application fields of smart agriculture based on the Japanese literature review. Now look at the figure. The big data module is designed to establish an indicator system and collect data pertaining to farming environment. Farming environment, air weight from sunshine, precipitation, soil. Then number second is farm indicators, which is agriculture traits, field management, and then data processing. Data processing includes ICT, AI, IoT, RT, and cloud computing and data meaning different latest trends and technologies. This comprehensive data collection serves as the foundation for data meaning and analysis of relationships between variables. It facilitates the optimization of agricultural production by uncovering insights and contribute to the enhancement of farming practices. Now look at some surveys which were performed in 2022. In the updated catalog for smart agriculture technology by MAFF encompasses 288 items currently under development or available for purchase, specifically tailored for crop planting. Among these 80 items cater to both rice and cultivation and the open air cultivation of various grain crops, vegetables and flowers. Additionally, 40 items are exclusively developed for rice planting, contributing a total of 120 smart technologies applicable to rice cultivation, representing 41.7% of the overall catalog. This underscores the close alignment of Japan's smart agriculture technology within the structural needs of agriculture product planting with a primary focus on advancing technological progress in staple agriculture products. Now look at the figure. This figure shows the number and figure 2.2 number and percentage of smart agriculture technologies for different crops in Japan in April 2022. So after analyzing the data presented in the table, these smart technologies are designed for application in three different scenarios, 333. Seeding and transplantation constitutes the largest proportion of 36.3%, emphasizing the pivotal role of paddy planting in driving technological advancements in Japanese agriculture. Other significant application scenarios in descending order of quantity proportion include application of chemical fertilizers and pesticides, which is 14.7%, harvest, shipment, and coordination, 12.3%, as well as tillage and farmland preparation, 10.5%. The smart technologies in question support 362 types of operations in agricultural production and management. In response to the practical needs stemming from an aging agriculture labor, force and considerable ratio of mountains and farmland, automotive driving and workload reduction claim the large percentage of at 36.2%, reflecting the fundamental technical characteristic of smart agriculture. The second ranking category comprises sensing and monitoring operations. Now, combining various individual technologies, a range of predictive models for crop growth and yield have been implemented, yielding notable economic benefits in Japan. Notably, smart production models tailored for large-scale rice farming stand out as detailed in table. Many of these models are domestically developed, while others are sourced in international organizations such as International Benchmark Sites Network, Agrotechnology Transfer, IBSMAT, and the International Rice Research Institute. Now, figure 2.2 number shows the number of agriculture technologies of different operations types in Japan in April 2022. The application of these models has significantly contributed to the enhancement of rice field in Japan. For example, after 2 year application in 50 hectares of rice fields, the Smart Agriculture Machinery Systems SAMS demonstrated its value by achieving a 20% reduction in fertilizer usage while increasing yield by 30% compared to the conventional management practices. Figure 2.2 shows the comparison of average working time between smart and conventional farming in Japan. Now look at the empirical analysis. As depicted in figure, the empirical analysis were primarily divided into three segments. The inputs, look at the figure, the inputs, output, and results. This input encompasses the determinant variables outlined earlier, including state-specific water temperature and depth. Now look at the output. Outputs consisting of rice fields represented by Y1 through Y6 as delineated in figure, and assessment of production efficiency was carried out using data envelopment analysis DEA. The findings are presented in terms of notable yield determinants and interactions between output and inputs, and slack analysis aimed at mitigating inefficient inputs and outputs. Now, our third review article is about electrochemistry, role of smart technologies in electrochemistry. Turek Rickard in 2023 developed electrified chemical manufacturing systems by using smart technologies. As the cost competitiveness of renewable electricity with fossil fuel energy sources increases and environmental concerns grow, there is a growing preference for transitioning to electrified chemical and fuel synthesis pathways. However, the conventional trajectory for electrochemical systems to achieve commercial scales has historically spanned many decades. The challenge in scaling up electrochemical synthesis processes primarily arises from the complexity of simultaneously decoupling and controlling the intrinsic kinetics as well as the effects of charge, heat, and mass transport within electrochemical reactors. Effectively addressing the challenge necessitates a shift in research methodology from relying on small datasets to leveraging digitalization for the rapid collection and interpretation of large, well-parameterized datasets utilizing artificial intelligence and multi-scale modeling. In this perspective, we introduced an emerging research approach inspired by smart manufacturing to accelerate the research development and scale up of electrified chemical manufacturing processes. The efficacy of this approach is illustrated through its application to the development of carbon dioxide electrolyzers. As renewable electricity becomes a more affordable option compared to the fossil fuels and concerns for the environment continue to grow, people are looking more and more towards using electricity for making chemicals and fuels. However, the process of making this switch with electrochemical systems had traditionally taken a really a long time to become widely used. The main challenge in making the electrochemical processes larger and more efficient is that it's tricky to manage several things at once, like how fast the reaction happens and how electricity, heat, and materials move within the machines doing the reactions. Figure 2.3 shows the vision of net zero carbon in future, and Figure 2.3 shows artificial intelligence and ML techniques for scale-up of carbon dioxide electrolyzers. So to solve the problem efficiently, researchers are changing the way they study things. Instead of using small sets of data, they are now using digital tools to quickly gather and understand a lot of very detailed information using things like artificial intelligence and multi-scale modeling. Now, in this perspective, we introduce a new way of doing research, which is inspired by smart manufacturing to speed up the process of figuring out how to use electricity for making chemicals. On a large scale, we show how this approach is valuable by applying it to the development of machines that use electricity to turn carbon dioxide into other useful substances. Here, the figure 2.3 shows a comparison between the smart approach and traditional approach. So this plan can be divided into four main phases, each marked by different background color. In first phase, shows in blue, we adopt the experimental reactor to automate data collection and enhance connectivity. This helps improve how quickly we can conduct experiments, assess data, and collect information. To do this, we need to choose a reactor that gives accurate data suitable for modeling. This means picking a reactor with well-defined transport characteristics. The second phase, highlighted in orange, involves using machine learning, ML, and artificial intelligence, AI, along with dimensional analysis to speed up the processing. This helps us uncover the relationships between inputs and outputs. These relationships are then used to create real-time control schemes and predictive models for the reactor. Controlling the reactor in real time helps confirm the relationships we have found, as proper control requires a good understanding of how the reactor performs. In the third phase, marked in green, we use multi-scaling modeling techniques. These techniques use fundamental relationships and relationships uncovered in the second phase to create. Figure 2.3 shows the smart manufacturing inspired framework. Scaling up emerging carbon dioxide electrolyzer technologies has proven to be challenging due to intricate interactions involving mass, charge, and heat transport intervene with complex reaction pathways. Addressing the formidable task of scaling up electrochemical synthesis methods necessitates a comprehensive scientific strategy that integrates highly experimental results with extensive data and advanced modeling techniques spanning from the atomic to the reactor scale. In this perspective, it assesses an approach designed to expedite research and the scale-up for complex electrochemical reactors, drawing inspiration from the same techniques employed in smart manufacturing to handle intricate process optimizations within the industry. This approach not only enhances research methodologies, but also establishes pathways for concurrently developing strategies to apply SM in industrial electrosynthesis. Processes predictive models of the reactor. This step helps to develop modeling methods to understand the local processes happening at different interfaces, like where gases and liquids meet or where liquids and solids interact. The models are then used to improve how we design reactors. So finally, in the last phase, highlighted in red, we use the insights gained from the modeling methods to guide the thoughtful design of prototype reactors. These designs can be tested virtually using the methods developed in the third phase before actually building them. This approach helps save cost and time. So, to summarize, scaling up emerging carbon dioxide electrolyzer technologies has proven to be challenging due to intricate interactions involving mass, charge, and heat transport intervene with complex reaction pathways. Addressing the formidable task for scaling up electrochemical synthesis methods necessitates a comprehensive scientific strategy that integrates high fidelity experimental results with extensive data and advanced modeling techniques spanning from the atomic to the reactor scale. In this perspective, it assesses an approach designed to expedite research at the scale-up of complex electrochemical reactors, drawing inspiration from the same techniques employed in smart manufacturing to handle integrate process optimizations within the industry. This approach not only enhances research methodologies, but also establishes pathway for concurrently developing strategies to apply smart manufacturing in industrial electrosynthesis processes. Now, our last is article about role of smart technologies in cosmetic industry. P. Escobedo in 2022 worked and created smart face masks in clinics and pandemic. The global recommendation for the general public to use face masks as a preventive measures against SARS-CoV-2 spread is widely acknowledged. While there is substantial evidence supporting the effectiveness of face masks in reducing community transmission, there's also consensus regarding the potential negative effects associated with prolonged use, particularly related to carbon dioxide rebreathing. In this context, we present the development of sensing platform designed for real-time monitoring of gaseous carbon dioxide levels inside FFP2 face mask. The system integrates an optochemical sensor with a flexible battery-less near-field enabled tag, providing a resolution, a limit of detection of 103 and 140 ppm respectively. The sensor's lifespan is 8 hours, aligning with the recommended usage duration of FFP2 face mask. Additionally, a custom smartphone application is included for wireless powering, data processing, alert management, and displaying the sharing results. Through performance tests conducting during daily activities and exercise monitoring, we showcase the platform's utility for non-invasive wearable health assessment. Moreover, its potential applicability for preclinical research and diagnostic is demonstrated. To counteract the rapid global spread of severe respiratory syndrome coronavirus 2, the virus responsible for COVID-19, the widespread adoption of face masks has been mandated by a majority of countries. Initially recommended by the World Health Organization for specific scenarios like crowded or enclosed spaces, this guidance quickly expanded to encompass nearly all situations involving non-cohabitant individuals in shared common spaces. Recently, a report presented a simple mathematical and demonstrating the efficacy of limiting virus transmission under conditions of low viral load. This development has sparked considerable debate about the actual effectiveness of face masks in disease control versus these potential adverse effects. This report does not aim to directly address the controversy, but rather to devise and assess a battery-free and wearable solution of determining carbon dioxide concentration within the dead space volume (DSV) of filtering face piece FFP2 face mask. It's essential to note that recent studies indicate SARS-CoV-2 is evolving towards a more efficient aerosol generation, and loose-fitting masks may offer only modest source control. Physiologically, DSV is defined as a volume of ventilated air with no significant gas exchange of oxygen and carbon dioxide. While standard face masks primarily function in air filters for the nasal and for mouth passages, integrating sensors to monitor relevant parameters can enhance their utility and effectiveness. Now look at this general design of that face mask. The design criteria for the proposed system align with commonly found in IoT devices, emphasizing sensing, connectivity, integration, compactness, scalability, low energy consumption, and affordable cost. The system's overall concept is illustrated in figure and supplementary movie. It comprises an NFC tag printed on a transparent, flexible substrate positioned on the inner face of FFP2 type face mask. System facilitates carbon dioxide measurement through a deposited chemical sensor with a fluorescent response. Real-time results are displayed on an NFC-enabled smartphone application with the smartphone approaches. As usual, you can look at the figure. The figure shows overview of NFC-based smart face mask of wireless carbon dioxide real-time determination. If you look at the A, flexible NFC sensing data, B, carbon dioxide sensitive membrane is used, and number C, smartphone app. So the optochemical carbon dioxide sensor is constructed by combining a stable inorganic phosphorus with an acid-base indicator that modulates the luminescence through an inner filter mechanism in response to the gaseous carbon dioxide acidity. This sensing cocktail is optimized to reduce interfacial tension and enhance carbon dioxide gas permeation. Importantly, the NFC-based system operates entirely passively, eliminating the need of our battery. Instead, it harnesses power from the near electromagnetic field induced by an external NFC radar, which can be any NFC-enabled smartphone paired with a custom-developed app. This setup allows for virtually immediate real-time measurement of carbon dioxide gas concentration upon smartphone approach. However, the continuous monitoring depends on the smartphone's NFC reader for power. Nevertheless, the system's battery-free nature is achieved through the use of electronics designed with ultra-low power consumption components. So that's all about the review articles. Now look at the chapter number 3, in which we discussed all this article. So the first point is discussion. After studying the literature, we find that the world is changing fast, and if you will not innovate your business based on current demand, your business could get into trouble. So think, connect, and innovate and adopt smart technologies in all industries. Smart techniques not only save time and increase yield, but also increase safety. With the increasing automation and digitalization of the chemical manufacturing industry, prioritizing safety has become more paramount than ever. Chemical manufacturers are making significant investments in safety training and equipment to ensure that the workers can adeptly operate and maintain new equipment and systems without compromising safety standards. Additionally, the industry is integrating advanced technologies like sensors and predictive analytics to proactively identify and prevent safety incidents before they manifest. The chemical industry, with a workforce exceeding 20 million in annual revenues approaching 5 trillion, and plays a pivotal role in supporting various industrial sectors such as agriculture, pharmaceutical, automotive, construction. These industries heavily rely on the steady supply of diverse chemicals to function effectively. Consequently, as these sectors progressively embrace smart manufacturing practices, it becomes imperative for chemical companies to innovate their manufacturing processes to align with future standards. Beyond the stringent conditions necessary for ensuring quality and efficiency, chemical companies routinely navigate regulatory compliance is an integral aspect of their standard procedures. Ensuring seamless connectivity of traceability data across the entire business becomes crucial for achieving this. Hence, smart manufacturing innovations should not only contribute to upholding stringent quality controls, but also provide accurate product information. Moreover, they must adeptly gather extensive data from disparate operational processes and swiftly offer meaningful and actionable insights. Smart manufacturing offers a solution for harmonizing rigorous regulatory controls and integrate functions with the value chain by leveraging automation and flexible networks. This is accomplished by integrating diverse digital and AI technologies, including computer vision, machine learning, deep learning, into the fundamental manufacturing system of a chemical company. Smart manufacturing networks derive advantages from heightened adaptability, swift design, adjustments, and a more flexible approach to a technical workforce training when implementing the smart manufacturing process. Now look at the chapter number 4, which is conclusion. So in this chapter, I conclude all my article review and all about this paper. Conclusion is the study was focused for the production of chemicals by using smart techniques. It increases yield and gives better quality results. Smart manufacturing represents a novel paradigm that enhances work intelligence and connectivity, introducing speed and flexibility through the integration of digital innovation. In the contemporary landscape, the digital innovation is intricately tied to sustainability of companies, forming an inseparable synergy rooted in the concept of circular economy. Digital innovation facilitates a circular economy model, advocating for the adoption of solutions such as digital platforms, smart devices, and artificial intelligence to optimize resources. Therefore, the objective of this research is to conduct a systematic literature review on the enabling technologies that can drive the development of new circular business models. So now I discuss some job opportunities. The employment landscape in the chemical manufacturing industry is poised to undergo significant changes due to the emerging trends in Industry 4.0 and the ongoing digital transformation of manufacturing processes. Anticipated shifts include surge in demand for specialized skills. Number one is the integration of Industry 4.0 technologies will necessitate a greater workforce skilled in operating and maintaining automated and digital systems within the chemical manufacturing sector. Proficiency in data analytics, artificial intelligence, machine learning, and automation is anticipated to be in high demand. Now, evolution of job roles. With the increasing prevalence of automation, certain manual labor positions in chemical manufacturing may be automated. However, this shift will create new job roles focused on developing, implementing, and maintaining digital systems. Individuals in these roles will need to possess high-level skills and adaptability to keep pace with the industry's rapid evolution. Next point is heightened emphasis on safety. The growing automation digitization in the chemical manufacturing industry will elevate the importance of safety measures. Workers will undergo training to safely operate and maintain new equipment and systems, so potentially leading to increased demand for safety professionals within the industry. The next point is amplified focus on sustainability. Escalating pressure on the chemical manufacturing industry to diminish its environmental impact is expected to drive increased demand for workers with expertise in sustainable manufacturing processes and technologies. And the last point is the future challenges. Which future challenges we will face in smart manufacturing? So the future challenges are the global disruption of supply networks has had a severe impact of everyday challenges of chemical manufacturing. In this regard, the first point is reducing formula cost. For chemical manufacturers to succeed, getting the right raw material is crucial. They stick to rules and specifications to ensure they are buying the correct ingredients. Make sure about the ingredients, managing purchase costs, dealing with seasonality, and adhering to maintenance constraints. This task becomes even more challenging when there are disruptions in the supply chain. Next point is handling different company product lines. The chemical industry faces ongoing challenges for diversifying its products. In this sector, companies are constantly merging and acquiring others. It's crucial to keep track of these changes. So the chemical manufacturers need to accommodate new competitors and consider the impact of globalization, adding new products while adjusting to existing ones requires continuous adaptation. So that's all about this review topic. Thank you.